Dr. Travis Scholten joining us from IBM. Dr. Travis works as a technical leader for public sector at IBM Quantum. He focuses on large strategy activities with government entities to identify opportunities for advances in computational quantum science to drive technical, economic, and social impact. In prior roles, Travis also developed and led research collaborations with startups, with enterprises on topics related to quantum benchmarking and applications. And with that kind of background, I'm sure he'll be the perfect person to get you all excited about why this program is even important, why you all should be caring about quantum algorithms, why do they matter to study today, what is the future of quantum software, quantum algorithms, and all of these surrounding areas. Travis also used to serve on the board of directors for Unitary Foundation, as well as the Economic Ecosystem Advisory Board for Superconducting Quantum Materials and Systems Center at Fermilab. Travis was also a policy hacker fellow with the Foundation of American Innovation. Travis is also the creator of Quantum Stack. Feel free to share your screen. And we are all very excited to hear what quantum algorithms are currently relevant, what is the future of quantum algorithms, and why should anyone care about this topic today?
Sure. Thank you very much for the very kind introduction, and hello, everyone. Happy to have some time today to talk with you a little bit about quantum algorithms, IBM's perspective on developing quantum algorithms, quantum advantage, quantum utility, etc. So I thought as a good motivation topic, what we could do is just take a brief look at the number of known quantum algorithms through this thing called the Quantum Algorithm Zoo, as compiled by Stephen Jordan, a quantum computing researcher. And the number of unique entries in this zoo is rather small, actually. It's only about 76. If you think about it, since the beginning of the quantum computing research activities, to only come up with order 80, maybe 100 if we're being generous, algorithms that leverage quantum computers in interesting ways is sort of a testimony to sort of the difficulty in developing quantum algorithms and getting a handle on where quantum computers can make, technical and scientific impact. And so one of the things that's really exciting these days is the new ways in which industry in particular has been trying to advance the idea of developing new methods for quantum algorithms. Okay. So let's just ask a very obvious question, like, what is a quantum algorithm? And I'm going to give a definition that I think is very operational and practical in nature, and also highlight some of the unique ways in which hardware, software, and science all come together in the service of developing new algorithms. So a simple definition could be all quantum algorithms involve defining a quantum circuit, which is the fundamental unit of computation, to be run on quantum processing units, QPUs, to then run them, and to classically post-process the results. All of the algorithms in the quantum algorithm zoo could be understood in this way: circuits, QPUs, running them, and post-processing results. So let's kind of break that down a little bit. So I said a circuit is the fundamental unit of computation, and a circuit we can think of as having two kind of fundamental properties that characterize it. One is a circuit width, which if you draw out a circuit, usually it's kind of denoted vertically. This is sort of the number of, this is the number of qubits that that circuit acts on. And the complexity is the number of non-trivial gates in the circuit. And we can tend to think of these as 2-qubit gates or other kinds of special 1-qubit gates necessary for fault-tolerant quantum computation. And one of the interesting things about quantum circuits is that, of course, you could simulate them classically, right? You could write down the circuit, you could write down all the gates, you could learn the math of the matrix multiplication in order to do that simulation. There are other kinds of simulation methods. And what you end up realizing quite rapidly is that if your circuit widths are maybe on the order of 50 to 60, possibly 70, those are actually kind of somewhat straightforward to simulate. Circuits that act on at least maybe 25 qubits, you could definitely simulate those using your laptop. For circuit widths that are approaching about 100, simulation becomes increasingly challenging. This is because if we do a brute force classical simulation, simply put, the amount of memory that we would have to have in order to store the state of our quantum system as the circuit is evolving it is very, very large and prohibitively large. Of course, for special kinds of circuits with special kinds of properties in certain kinds of situations, you can develop approximate methods that can help you simulate the action of that circuit. And at IBM, we've been talking about this concept for a couple of years now of the utility frontier, which is circuits that act on at least 100 qubits, where they are well beyond what you could brute force classically simulate, although maybe some classical approximation methods exist. And that's kind of the era that we wanted to be in, that we've been pushing to develop, is this notion of quantum utility, very high width circuits. And we'll get to talking about high complexity circuits in a couple slides. Now we have to run quantum circuits on something. And so we need quantum computing hardware. And IBM has been pioneering the development of bringing useful quantum computing to the world. Pictured here is an IBM Quantum System 2. It's located just under, well, kind of just underneath me in the lab building that I'm currently sitting in. This is a quantum computer that's hooked up to the cloud that members of the IBM Quantum Network can use to run circuits and develop interesting applications, et cetera. And so we've been building out these quantum computing systems and hardware in order to run circuits, to run them reliably, to run them in a performant way, to run them with high availability and uptime, and to run them in a scalable way. Here, scalable means we can scale out the hardware in terms of the complexity of the circuits that it can run. And then we have to classically post-process the results. And when we think about that statement, it immediately lends us to realize that, well, quantum algorithms are always going to require classical computers. And I think this is a very important point because sometimes people, they sort of miss the fact that we need classical computers to both operate quantum computers, but also to take the results that we get back from a quantum computer, post-process it, develop new circuits that need to be run. Classical computers are the interface points by which end users gain access to quantum computers, typically over the cloud. And so quantum algorithms will always require classical computers. This presents an interesting opportunity, though, as classical computing hardware advances, as new things like AI infrastructure comes online, where we can say, well, how do we leverage the best-in-class capabilities of each kind of computational capability to solve pressing computational problems? That is, there are lots of things that classical computers can do very well. They can diagonalize matrices very well. They can do lots of arithmetic, et cetera, et cetera. There are things that quantum computers can do well. They can run certain kinds of quantum circuits in ways that are difficult for classical computers to emulate or simulate, et cetera. There are different kinds of computational problems that quantum computers are good for versus classical computers. And so when we talk about quantum algorithms, we should be really asking the question of, well, we have both of these compute capabilities. How do we leverage them in the right ways together in order to achieve maximum, technical impact, scientific results, et cetera? And so for this reason, at IBM, we've tended to think a lot about how the future of computing is really heterogeneous in nature. It's not just that we have quantum computers and then we have classical computers and then we've got like little AI supercomputers. It's that we have a whole compute fabric and that we need to intelligently orchestrate computations across that compute fabric to make it easy for end users to develop novel applications, to do interesting kinds of scientific research, et cetera, where again, we're leveraging the best in class of what each of these capabilities can bring to the table. And so with this backdrop on infrastructure, okay, I want to make a slight pivot. And I want to talk a little bit about, okay, well, suppose that you've built all this fancy schmancy hardware and you've made made it available to the public, et cetera. Like, what do we expect people to do with it, et cetera? Okay. Well, we have this idea that we plan to increase our capabilities for running high width, high complexity circuits over the next several years. And so over the next 4 years, we envision, certain key milestones in our program that will, again, increase our ability to run the kinds of really interesting quantum circuits and new kinds of quantum algorithms that end users are developing. I think there's only two on this list that I'm going to highlight specifically. One is in 2026. We anticipate demonstrating quantum advantage. I'll say that again. In the year 2026, we anticipate demonstrating quantum advantage. Now, where exactly will quantum advantage come out? That's still a little bit TBD, and we have researchers that are working very hard to identify interesting computational subroutines where quantum advantage might be had. We have people working with enterprises and universities and startups to identify interesting application areas where maybe those computational subroutines can be applied, et cetera. But when we think about sort of the future of quantum computing, that future is actually sort of coming to us at an increasing rate, as it were. That industry has been advancing, tremendous advances, especially over the past decade, et cetera. And this notion of, quantum advantage by 2026, it's actually kind of a realistic thing to be saying these days. And then the second milestone is in the year 2028, we plan to demonstrate the first error-corrected quantum computer. Now, by 2030, we plan to have deployed the world's first error-corrected fault-tolerant quantum computer. So this is just basically the same way of looking at the previous slide, but just through an image of our current IBM quantum roadmap. Again, we've had this vision from the beginning of, we wish to bring useful quantum computing to the world. We've done that by making quantum computing available over the cloud, et cetera, et cetera, et cetera. But looking forward to the future, we are really excited about our ability to deliver on error-corrected quantum computers in 2029 with Starling class systems, 2033 with Blue Jay class systems, and beyond. Now, you might be looking at those two slides and you say, wait a minute, okay, Travis, so you just said in 2026, demonstrate quantum advantage. And then in 2029, you said deploy the world's first fault-tolerant quantum computer. But I thought that attaining quantum advantage would require fault tolerance, right? Yes, what? Not exactly. And it all comes back to this question about quantum circuits and their complexities. We had this first evidence of the idea that, well, quantum computers are becoming increasingly useful tools for computational science with a Nature paper that we published in 2023, this evidence for the utility of quantum computing before fault tolerance. And the idea behind this paper was to really push the capabilities of the hardware and the software stacks that we were developing to use these techniques called error mitigation, which let a noisy quantum computer emulate a less noisy one. And using these error mitigation techniques and advanced hardware, we could get a quantum computer to produce accurate answers in problem regimes, be it where brute force classical computation would not work. Again, that's at above 100 qubits from the previous slides, and also where classical approximations start to struggle. Another way of looking at this work was to really understand, well, if we have to use classical approximate methods, then wouldn't it be good to have methods where I can have provable error bars on the outputs that I get from those methods? And so we developed these error mitigation techniques that let us do so. And when we look at the results that we get back from our error mitigated quantum computer and also classical approximation methods, they all are roughly comparable to one another. And that's actually genuinely interesting from a scientific standpoint. And then since then, we've enabled other researchers to do experiments at that scale, to run circuits at that, order 100 qubits or so, plus or minus, let's say 20, and with a large number of non-trivial gates. Here we're indicating the number of 2-qubit gates. We've made these systems available over the cloud. It was actually a little bit radical a couple of years ago when we did that, because we said, well, from now on, we shall never put any quantum computer that is less than 100 qubits on the cloud. And we shall only use quantum, we will only make available to the public quantum computers that are, have at least 100 qubits, et cetera. And so this, I think these results from the research community are validating that, well, if we bring interesting hardware and we make it easier for people to develop interesting kinds of quantum circuits, then they can do interesting science. And that might, help accelerate the development of attaining quantum advantage. And the reason why that is the case is this kind of quantum advantage regime, if we can call it that, exists in an interesting space. It exists in a space which is before fault-tolerant quantum computing, where we could run the different kinds of algorithms from that quantum algorithm zoo and other kinds of algorithms too. And it's beyond what just classical brute force computation is capable of doing. And so it exists in this weird middle, where the only thing that I can really do if I wanted to use a classical computer to solve the problem is I can either try and approximately simulate my quantum circuit, or I could have some classical approximation method in general, right? Like if I'm doing like a spin physics sort of problem, maybe there's some mean field theory that I could apply in order to gain some insights about the problem. And so it's in this regime, where the circuit complexities are beyond what you can do classically, but are not so complex that they require a fault-tolerant quantum computer in order to run them reliably, that this is the place over the next several years, by the end of 2026, right, where we expect it is reasonable that we could find quantum advantage. Okay? And so it's a very interesting time in the field in that regard, right, for our, the capabilities of the hardware, the capabilities of the software, and now this increasing focus on, well, can we really find some interesting place to look for quantum advantage? Now, another reason why I think it's important to talk about this notion of quantum algorithms, not just for the sake of finding interesting ways to attain quantum advantage, is that sometimes people make these plots like the one on the right here of different kinds of resource estimates that ask, well, what is this complexity and scale of the circuit that I would need to run in order to solve a problem? And there's this logical fallacy called conflating the map with the territory. That is, just because somebody makes a plot like the image on the right, doesn't necessarily mean that that is the entirety of the story when it comes to quantum applications and algorithms. And I think there's three things to keep in mind when people talk about resource estimates in that regard. The first is there are quantum computers available, and you could potentially do interesting things with them if you get access to them. The second is that working on algorithms research, the study of quantum algorithms, in a pen and pencil paper fashion sometimes using access to quantum computers, that should enable both new kinds of quantum algorithms, but also new kinds of quantum applications. And then the third point, and this relates to the infrastructure point from a couple slides ago, is we've really at IBM have been thinking a lot about this notion of multi-circuit algorithms, where we can use quantum and high-performance computing. So a lot of the times when people think about a quantum algorithm and a quantum application, they say, okay, well, take Shor's algorithm, right? I'm going to factor an integer. Well, I need to run a very high width, very highly complex circuit. And the scale and complexity of that circuit is such that only a fault-tolerant quantum computer could run that thing. Definitely the case. But what if there were interesting applications where maybe instead of having to run one very large monolithic circuit, I could run a bunch of smaller, less complex circuits and leverage classical post-processing of those circuits and the results that they give me in order to effectively solve the self-same problem. And so this notion of multi-circuit algorithms is extremely important going forward for the field. Now, I do want to give a couple of examples here of like things that people have been doing in the literature to again motivate like why quantum algorithms. I think one, this is an example from the UK, a UK-based startup called Phasecraft. They've been doing incredible work. Their sort of byline is the quantum algorithms company. So there you go. And so what they did is they studied some problems in materials science, where in this plot on the right, the gray dots on the rightmost side of the figure are the resource estimates that they came up with for a variety of material science modeling problems. And then what they did is they said, well, like we know the physics of materials. Maybe that can help us design a new kind of quantum algorithm or a new kind of encoding method. And then lo and behold, when they used those new innovations, all of a sudden the resource estimates went down. Okay. So I'd say, again, we've already seen how improvements in quantum algorithms can simplify circuit complexity. They can take problems which would have required circuits that are so complex that they would require very far future quantum computers to run them and help move those applications closer to the present. So that's one example of why quantum algorithms matter. Another example, and I'll be very candid here. I'm not exactly sure how much fruit this would yield, but I think it's an interesting idea. Is there's been a lot of work over the past several years, probably past decade, I'll be a little bit more generous, of trying to understand like what are certain kind of computational ideas that are applicable across many different kinds of quantum algorithms. And so people have been investigating things like quantum signal processing, the quantum singular value transformation, et cetera, to really develop a unified framework about this is a quantum algorithm from the computational subroutines perspective. And I think it would be really interesting for people to go back and now look at different kinds of quantum applications in light of these new computational subroutines. And maybe they could help us understand, here's why we expect to find quantum speedups in these applications. And here's where we should look for them. And here are the obstacles to maybe realizing them, et cetera. So again, another reason why quantum algorithms are super interesting. And then the third, and this comes back to this point from a couple slides ago, is this notion of multi-circuit algorithms that leverage what we've at IBM have pioneered calling quantum-centric supercomputers. So if we go back to that the last hardware slide where we talked about the future of computing is heterogeneous, a way of thinking about what that infrastructure is it is a supercomputer where it's not just a supercomputer because it has, very high-end, fancy classical compute, but maybe it has new kinds of AI infrastructure and different kinds of ASICs and AI-specific chips. And maybe it has some, large-scale, medium-scale quantum computer attached to it. And all of these computational modalities are talking to one another and they're interacting with one another. And there's a software layer that sits on top of that helps orchestrate those computations, et cetera. And so one way why we can think of these, why did these multi-circuit algorithms make sense from why should we look at a perspective, is actually to go back in the literature. And there have been lots of kind of multi-circuit algorithms where the way that worked is a classical computer would propose circuit by circuit, a circuit to run on a quantum computer, and result by result, generate a new circuit. And so these are things like the quantum approximate optimization algorithm, the variational quantum eigensolver, et cetera. Now, the new idea has been to say, well, okay, this can get a little bit tricky sometimes, especially when trying to operationalize it in a software stack. And so the new idea with these quantum-centric supercomputers is you leverage large amounts of problem-specific quantum computation and then large amounts of problem-specific classical co-processing. And maybe you have to iterate those kind of big processing loops a little bit until convergence. And so our team has actually been working on this quite hard, and they have this really interesting paper out called Chemistry Beyond Exact Solutions on a Quantum-Centric Supercomputer, which introduces a new kind of quantum algorithm that takes advantage of best-in-class from quantum capabilities and best-in-class from classical HPC. This is a collaboration that we did with Riken, which is a computational center in Japan, and they run Fugaku, which the last time I checked was one of the top 5 most powerful supercomputers on Earth. And so these two teams figure out some really interesting ways to leverage the full capabilities of one of the world's most powerful supercomputers and the full capabilities of some of the world's best quantum computing hardware to do interesting quantum chemistry calculations. And this sample-based quantum diagonalization algorithm, we'll go into it in detail in a couple of slides, what it let us do was it let us solve these kind of estimating ground state energies for various interesting molecules in a total amount of time, here 2 hours, which is way less than doing something like the VQE, which would have taken almost 3 million years, or even using a future fault-tolerant quantum computer, which the team estimated that might have taken almost 13 days of runtime. And so this raises a really interesting point. Like, oh, so by using quantum and classical together at this interesting scale, we can tackle interesting chemistry problems in ways which are competitive with not just the current ways in which people do things like VQE, but also future things. Okay? Now, in a little bit of detail here, the essential idea is that you can use a quantum computer to generate samples, right? Get a bit stream back. Now, for various kinds of chemistry problems, we might have some a priori knowledge about the problem. For example, we might know, the total number of particles or electrons that we're trying to deal with here. But because of noise, the answer we get back from our quantum computer will be corrupted. And it might not do things like obey particle conservation. Well, you can use a classical computer to try and guesstimate, well, okay, this is what the quantum computer gave me, but if it had less noise, then maybe this is what it would have given me in a way where that result obeys particle conservation. And then you can project your Hamiltonians onto those corresponding states, and you can diagonalize matrices using classical HPC, and you can essentially try and recover what was the actual particle conserving state that the quantum computer should have produced, and then you can use that in your ground state estimation algorithms classically, and you can repeat until convergence. And I will give a shout out here. So the Qiskit YouTube channel, you can find something from Javier, a Qiskit quantum seminar in more detail on this. And since that work that we've done, we have pioneered not just working with Riken, but also working with the Cleveland Clinic, working with Lockheed Martin, to again expand the usefulness of this SQD algorithm in other kinds of quantum chemistry calculations. And again, so this validates the idea that this is a new way to do quantum chemistry, different than how we tended to do it before, and in a way which doesn't require fault-tolerant quantum computing. And there have been other kinds of multi-circuit algorithms that the team has been working on. I'm not going to go into these in any detail here, but I just want to emphasize that from a research perspective, what our team has been most excited about is new kinds of quantum algorithms leveraging HPC and quantum computing, where we are using multiple circuits that can be run efficiently and quickly using a quantum computer. We get back a lot of results from a quantum computer. We classically post-process them using HPC, and that lets us do interesting things. And so what this tells us is that really in this kind of in-between era and towards, kind of like early scale fault-tolerant quantum computing, there is a tremendous need for new kinds of algorithms. Because the way that we did things, right, like 13 million years with VQE for that quantum chemistry calculation, that's not going to be feasible. So we need new ways of doing things. We want to make today's and near future quantum computers increasingly useful. And so we need new quantum algorithms to do that. Now, you might be sitting there saying, okay, Travis, this is really great, right? But like, how do I, researcher or interested enthusiast, operationalize this idea? And so I'm just going to spend a little bit talking about the software stack that we've tried to develop and make available to the community in order to do this. And so I would say that research in applications and algorithms, you need software, okay, right? Because you need software to access quantum computers and you need software to run quantum computers. Goes back to our earlier point. All quantum computers require classical computers. Okay. And so we've been backing the development of something called Qiskit. It is the world's most popular software development kit as measured by an independent third party. And we're really excited for the community that has been developed around that and the various functionalities that we have been building through and around the Qiskit SDK to make it useful for scientific research. I'm not going to go into all of these pieces in a little bit of detail, but on the right is the overall perspective about the IBM quantum platform, starting from the bottom with hardware, moving up to an orchestration layer, again, that quantum-centric supercomputing, developer tools, and then abstraction services. So again, this Qiskit SDK is the core SDK. It's the thing that people like you would use to write quantum circuits and submit them to our IBM quantum processors. It's preferred by over 74% of the developer community. It has a large number of dependent projects on GitHub. So I'd say it's a really strongly integrated part of the quantum software ecosystem. Qiskit runtime is how we run quantum circuits efficiently. That's something that we take care of on our side. It's something that we use inside that IBM quantum system too, in order to run circuits for our end users. And then Qiskit serverless, right? Quantum computing is coming of age in the cloud computing world. And so we need to be able to orchestrate computations across QPUs, CPUs, and GPUs. And then we have these add-ons, which are also relevant for a researcher perspective, which take the research capabilities that we've developed, and we turn them into modular tools that let people design new kinds of quantum algorithms. So I have one slide on this, wrap-up slide. We can take some questions. So these add-ons really do accelerate researchers' ability to do innovative utility scale algorithms development. We take the research that we have done. We have a whole team of people who exist at the interface of research and software development, and they turn those research insights into software tools that other end users can do. And so, for example, here on the bottom, it took us about, let's say, a year to produce our first paper with Riken, and then we could compress that research using these tools into something like 2.5 months of time, which is a pretty strong acceleration, all things considered. Okay. So again, why are quantum algorithms, exciting? Why do they matter now? Because they all involve defining circuits, running them on QPUs, and classically post-processing the results. And this new world of, heterogeneous compute, quantum and HPC presents new opportunities for developing quantum algorithms. I'm obliged to give the shout out to go check out the IBM quantum platform, right? We make utility scale quantum computers available for free, so on and so forth. With that, I will say thank you very much for your kind attention. Happy to take some questions.
Thank you. We've already got a bunch of questions coming in from Discord, so I'm going to start reading a few out. So Travis, this one is from Hussein, and he asks, as the number of qubits increases, the space in which the optimizer is required to search in increases exponentially in algorithms following the variational approach. How is IBM handling this issue?
Well, to be very clear, right, that there's another way of saying what I said, which is that the brute force, the standard variational approach is not going to work long term, right? And that we've known that things like barren plateaus, narrow gorges, et cetera, in algorithms like VQE, quantum machine learning applications, QAOA, et cetera, right? And so in that sense, we don't view the variational algorithms like that as particularly useful, which is why we've been investigating these new quantum and HPC approaches.
Thank you. This one from Ron from Chicago. Are there cloud-based quantum gate simulators that can handle 70 plus qubits?
I'm not sure. We are not in the business of simulating quantum circuits. We're in the business of running them in a performant and scalable way on quantum computing hardware. Something NVIDIA, I don't know.
Albina from Italy. How do the IBM team decide which problems are worth pursuing with quantum algorithms versus just improving classical approaches? Is there some threshold criteria?
That has been a really interesting and robust topic of conversation amongst the team, especially in this pursuit of quantum advantage. And so, the thing is that what does it mean to attain quantum advantage is still very much a research question. So it's not as though there's some well-defined framework in the research literature where you say, well, just do A, B, C, and D in criteria, D, E, and F, and then you know whether or not you've attained quantum advantage. So you have to look at it very holistically. You have to look at it in terms of, estimating the complexity of the problem. You have to estimate what is the classical complexity, et cetera, and really try and identify it's more about identifying interesting problem regimes, scaling complexity of the problem itself, where you expect there might be some tip over point. But no, it's not like there's some turnkey approach to doing that in that sense. At least not right now. But who knows? Maybe in 5-10 years there will be.
Thank you. I think we have time for one more. Let's see what's come in. This is from Jeet, Maryland, US. Can multi-circuit quantum computing use entanglement? If not, how can it be useful in attaining quantum advantage?
That's a really interesting point. I'm taking a very broad definition of what multi-circuit algorithms mean, and the team has been investigating some set of techniques which are called circuit knitting, which allow us to essentially represent the entanglement across a partition of a large-scale quantum circuit using classical post-processing of subcircuits defined relative to those two partitions.
Thank you. I think that's all we have time for.
Sure.
Thank you so much, Travis.
Travis, we had over, I think, 450 participants live watching in your Zoom. But with that, we do come to the end of the session with Travis. Thanks a lot, Travis, for taking out time and sharing a good overview on why quantum algorithms are important, and more importantly, why it is important for all of you to study algorithms today.
Thank you so much, Travis. That was really great.
Of course. No, thank you. That was fun.